And we are recording. Okay, 1.2 functions and graphs. Okay. Gentlemen, are we ready or not? Good, it's recording. We just got to sit down there. So, independent variable, it's the input, usually x or t for time. We're going to do a lot of stuff in relationship to time. What's its velocity at a time? What's its position at a time? What's the acceleration at a time? How many potatoes do we have at a particular time? What is the number of people getting into line at the amusement park ride at a particular time? What is the rate of people getting into the line? Not how many people are in the line. What is the rate of the number of people increasing by? You know, is it increasing by 20 people per hour? You know, or whatever. And a lot of things in relationship to time in here. Dependent variable is the output. The value of this depends upon the input, usually y or position or something else. Your y is your dependent, x is your independent. You pick the independent, the other one's determined by what you plug into the formula or equation. Domain and range are huge in what we do in here. Domain and range are huge. We're going to be talking a lot about domains and ranges, where things exist, where they don't exist. We don't care about stuff that's not the domain. Okay? We're going to have a lot of formal definitions of things as we pass through this year. And often, those ones are dependent upon domain. Okay? Domain is the input of the function or relation. Independent is the independent variable. The domain is what can we put in? What are our possible values of our inputs? Okay, range is the output. What are we going to get out of it? What is our possible outputs? What are all our possible outputs? Now, some of the things we will talk about in this class do not work under all circumstances. But we are smart people in here. We're smart enough people that we will say, okay, we know it doesn't work, but we're only going to work with this domain here. We're going to ignore this stuff over here. We're going to ignore that stuff over here. And we're only going to work in this particular vicinity because we know what we want to do works here. And we will limit the domain on things. We will limit possibly our range. But mostly what we do is we say, listen, we know we can't talk about what's going on here. We can't talk about there. So we're going to just talk about within this particular domain. We only care about what's going on between this point and nowhere else. We're going to do a lot of domain restrictions. A lot of domain restrictions just to make what we want to do work. Okay? Any questions on this? Okay. A relation is a set of ordered pairs. Anytime we have a set of ordered pairs of any kind, it is a relation. That set of ordered pairs can come from literally a set of ordered pairs, which makes life coordinates. It can come from an equation that gives us x's and y's accordingly. If this is your x, this is your y. If x is this, y is that. That gives us a relation. A function is a particular kind of relation. Okay, not every relation is a function. Every function is a relation, but not every relation is a function. Not every equation is a function. Okay. A function is a rule of correspondence that assigns each element of an x in domain a unique element of a y in range. No two first coordinates of a relation are the same. Every x has a y. There are no two y. One x does not have two y's. Okay, one y may have several x's. Okay, the equation, the line y equals 5 is a function. When x is 1, y is 5. When x is 2, y is 5. When x is 3, y is 5. It's still a function. Each x has only one y to go with it. Okay, it is a function. You may have several. You may have one y for all x's. it's still a function. But if you have more than one y for any one x, it's no longer a function. If you have x, if you have, let's say, square root, technically speaking, the square root equation is not a function. The square root of 4 could be 2 or negative 2. But if we want to make it a function, all we do is limit the domain. Or actually, in that case, we limit the range. To make it a function, we limit the range. Hey, all our answers are only going to be positive. That makes it a function. Okay, and we'll do stuff like that. Okay, this is a mapping. I'm sure you've seen mappings before. Domain, range. So x goes to 1, x goes to 3, or sorry, 3 goes to 3, 4 goes to 3, 1 goes to 2. That's a function. This one's not a function because 1 has 2 corresponding y values in the range. Okay, you can't have 2 values for 1x. You don't have to have 1. They can have the shared one, but each one of these only has 1 on the other side. Okay? Questions? Okay, I'm sure you've seen the vertical line test before, right? Vertical line test, if you pass a vertical line over a graph, if the line touches the graph at more than any one point in the graph, it's not a function. Obviously, this circle equation right here, this is not a function because that vertical line touches more than once. It only has to happen at one time that it touches more than once. That is not a function. Okay. My question to you is the next one a function? Does it touch more than once or not? Yeah, it's not a function. Technically speaking, what's going on there, we have an issue with that flat spot. What happens when we circle in? It goes more than once. That one's a real iffy one, whether or not that's a function. Does it cross more than once or not? Does it touch more than once? Well, who says it's a function? Who says it's not a function? Yeah, I'd call it a function. I would. Because right there where it does, you have a horizontal tangent line, but it's only at that one spot where it doesn't have it. Yes.
I can tell it's like actually straight though. Like there's just like us.
You really kind of have to trust that it doesn't actually flatten out straight. And it's hard to tell from a graph itself. If I gave you the equation, we could tell for sure. But without the equation, it's hard from a graph. From this graph, can you tell for positive and for certain? No. But we got a really good idea because we know the types of functions that give us this graph. Cube roots. This is a cube root graph. Probably. I bet that's what it was that I used to make this. Cube roots are functions. Square roots are not. Cube roots are functions. Each x has a unique y. Because negative cube roots have negative y's. Positive numbers you take the cube roots from have positive y's. They don't share. But you can't really tell really well from the graph, because we know what they're supposed to look like. You'd probably say, yes, it is. Yes, it's a function. Hard to tell. But that's the iffy point right there. Sometimes you just can't tell. It's not obvious. You kind of have to have a little more information than what's going on with the graph. We are going to do a lot of work interpreting with graphs. Okay, interval notation. There is a ton of interval notation used throughout your textbook, AP test. I use them on the test. Okay, interval notation is what we use to determine domain and range for the most part. We're talking about domain, we talk about range, we usually give intervals. Okay? So, interval notation is closed when the endpoint is included. So if you have brackets, that means the point with the bracket is included as part of your domain and or range. That is part of the interval. Okay. Same thing. Brackets are the same thing as or equal to. If I have x is between 2 and 4, my interval notation for that is bracket 2, 4. 2 and 4 are included because it's or equal to, and everything in between. Okay? So a bracket is a closed interval. It means that the thing is included in it. An open interval means the endpoint is not included. If y is between 0 and 3, as an interval, that would be 0, 3 in parentheses. Because 0 and 3 are not included. If your domain or your range goes to infinity or comes from negative infinity, it's an open interval. Infinity is not a particular value. You cannot have it be included as that particular interval because it's not a particular value. Infinity is always open. Always open because it's not a particular value. Okay. Intervals can also be half closed. That is, open on one end and closed on the other. It's entirely possible one end is included and the other one's not. Okay. Going to use an awful lot of interval notation in here. An awful lot. You have to be comfortable with it. You have to be able to go back and forth between these. You got to know that they mean the same thing. Okay? You've got to be comfortable with this kind of stuff. Any questions so far? Okay. So let's see if I can get this slid up. Yeah, there we go. So take a moment on your paper, on your notes. Sort them out. Which ones are open? Which ones are closed? Which one are open and closed, left and right? Which ones have are closed on the left only? Which ones are closed on the right only? Because you can have open and closed both. Okay. So let's see. Closed left. This one. Closed right. And if I got this one right, that goes with that one anyways. And this goes with that one. Those are the same versions of the same thing. That's an open interval. This is closed right. This one's closed left. This one's a closed interval. This one's an open interval. That's the same as that. That's the same as this. Okay. From negative infinity to positive infinity. In other words, all real numbers. Everything's included, all real numbers. We do not work with complex numbers in this class. Okay. The calculus that works with complex numbers is not something we cover in here at all. You're welcome. Yeah, so that's a big one there. This one here, x is greater than or equal to -3, because it's -3 and everything larger. So as an inequality, it's not between the two numbers. It's everything bigger than that. So it's -3 and everything larger. Okay. Questions? Okay. So here's what I want you to do next for each of these graphs and the corresponding equation that goes with it. I want you to name the parent function. The parent function, in case you forgot, is the simplest version of that type of equation. So what is the simplest equation for a straight line? Y equals x. That's the parent function. Everything else is some twist or turn on the parent function. So the parent function for the first one is y equals x. And then I want you to give me the domain and range for each one of those four equations. You can get them kind of from the graph, but there's no real numbers on the graph. Better to get these ones because they have the equation, get the domain and range from the equation. Okay. So, first of all, the parent functions. We did the first one, y equals x. Second one, y equals x squared. Third one, y equals square root of x. Last one is 1 over x squared, because it's a little bit different than 1 over x. If you had 1 over x, it's not, because the square is a big deal. Okay, the square is a big deal on the x. You do need to include that. Okay. Your domains, all real numbers. I can plug anything into the first. I can plug anything in here. I can take any number times 3 and then subtract 2. I can take any number, subtract 3, square it, and then add 2. My domain on here, however, is limited. I cannot have a negative square root. I'm not allowed to have a negative number underneath the radical. So x has to be values that don't give me a square, don't give me a negative square root. So 4 will give me 0. So I look at what's going to give me 0, and then what's going to be positive, what's going to be negative. X has to be less than 4. Anything larger than 4 will make it negative underneath. 0 is okay.
For the third domain, like the bottom one.
That should be negative infinity, not positive infinity. Thank you. I'm hoping that's what you were saying.
Yeah.
That should be negative infinity. My bad. The last one, what am I not allowed to have? I'm not allowed to have 0 in my denominator. Okay. So anything that makes my denominator 0, no bueno. In this case, it's 0, so x cannot be 0. In notation form, negative infinity to 0, 0 to positive infinity with open bracket on the 0. That means 0 is not included. Much easier to write x can't be 0 than to put that one in interval notation, but you have to be able to understand both of them. Okay. The most common things, domain is going to be much more important to us than range. Don't get me wrong, range is important, but domain is going to be much more important to us in here. And the things you're going to be looking at is where do things not exist? What am I not allowed to have? You can't have something be undefined. So you cannot have zeros in your denominators. So anything that's going to make a denominator 0 in anything we deal with, that's going to be an important thing. Anywhere where I can't have a negative square root, I'm not allowed to have. That's going to be an important thing. Zeros and denominators are going to be a big deal for us later on. Okay, we're going to be looking for a lot of zeros. Places where things are equal to 0, places where things are undefined. And where they're undefined, 90% of the time, undefined comes from a 0 and a denominator. That's going to be a big deal for us later on. Okay. And then the ranges. All real numbers for the line. Y is greater than or equal to 2. If this is 0, the lowest it gets, and the graph gives you a picture of it, it can't get below a certain point, 2 or larger. Same thing on this one, it's from 0 to infinity. It kind of grows slowly, but it will reach, eventually it will reach towards infinity. X is going to have to be absolutely huge to get to infinity on the square root one, but it will eventually get there. And then the last one, y is greater than or equal to 2. And y will reach every value larger than 2. Yes.
Y is greater.
Okay, so if I look at this one here, it's undefined at this point. But if I put anything else in here, it's going to be 2 or larger, because it's a very good question. This will always be positive. It will always be larger than 0, right? Cannot be 0. The only way a fraction is 0 is if the numerator is 0, right? So this will never be 0. It'll get real close to 0, but it'll never be 0. It will always be positive because x squared is always positive, right? So if I have a positive number that gets close to 0, it'll do that. So yes.
So if it never reaches 0, you should.
Yeah, you just got, this should not be, this should be open. And that should be there. Sorry, my bad. Thank you for catching that. Thank you for catching that. I'm going to get a little sick. And here's what's going on. Normally I'd be handwriting a lot of this stuff out. But I got a bum shoulder, and I do not want to be writing any more than I have to right now until I get it cleared up. You know, it's one of those things I really don't want to do any more writing than I have to. I will. But part of the reason I typed this up this morning, and it's not as bad as when I did the Algebra 2 one the other day. Man, I love all rhythms with mistakes. I had to fix it, go back and fix it afterwards. It's more. But yeah, so now I'll fix those two. But yeah, you got to look at this. One of the things you have to look at, we're going to talk about where are things positive, where are the negatives. If you have something that's never negative, something that's always positive, that's an important concept to understand. If I'm looking at where something is positive or negative, I may be doing that, evaluating something strictly to see if the function is positive. Where is it positive? Where is it negative? Hey, this whole thing is always positive. That's an important thing to know. Okay. Okay, can this be 0? Can this part of it 1 over x squared ever be 0? No. So it will always be a little more than 0. Maybe an infinitesimal bit more than 0, but it'll always be more than 0. Because when x gets really big, x squared gets really big, this goes close to 0, but it never actually is 0 itself, is it? So I have something that's always a little bit more than 0 plus 2, so it will never actually be 2. It will always be just a little bit above 2. It might be an infinitesimal amount for all intents and purposes, and it actually is 2, and you get really far out there. It's, you know, it's close enough for government work, we can call it 2 when it gets really far out there, but by the same token, it not technically never actually is 2. What kind of behavior do we call that? Remember, this is going to be important in the next step. It's an asymptote. Now, that's asymptotic behavior. We're going to be discussing horizontal and vertical asymptotes in the next chapter, and how to find them and how to prove them. Okay. Questions on this? Okay. I'm going to pause this. Freak out everybody who just saw it change instantly when watching it on the video. Because they didn't see it work. It went from dark blue to light blue. It's like that. See, on the computer screen, it's fine, but up here, it's not. On the computer screen, it's real easy to tell the difference between those things. I sometimes forget and don't always have the right colors in the background. Okay, even and odd functions. I'm sure that you discussed even and odd last year as part of Freak Out. Okay. A function is, if f of negative x is equal to f of x for all x in the domain, then f is even. If you stick a negative number in, let's say you put in -2 and you put in +2 and you get the same output, that's an even function. Okay? For x and its opposite. If you put x and you put its opposite value in the function, you get the same value, it's an even function. Okay? It's symmetric about the y-axis. Okay? Y equals x squared is a great example of that. If f of negative x equals negative f of x for all x in the domain, then f is odd, is origin symmetric. In other words, you rotate it around the origin. Y equals x cubed is an odd function. Okay. So, even and odd, nice to know. You'll be asked to handle this coming up. Okay. So, one of the things you're going to do is you're going to be asked, is it this? Is it that? Does it fit this criteria? Does it fit that criteria? Is f of x equal to 3x to the fourth minus 2x squared plus 5 even or odd? Here's how you tell. Put in negative x and see what you get. You get that back again? Or do you get the opposite of that? If you get this back again, if you get this, the same thing back again, it's even. If you get the exact opposite of that, change the sign of everything, then it's odd. Bless you. Only one way to tell. Plug it in. Okay. So negative x to the fourth power is positive x to the fourth power. It's an even power. 3x to the fourth. X squared, negative x squared is the same thing as positive x squared plus 5, which equals f of x. Therefore, it's even.
What if 2x squared was 2x to the third?
Okay. Not everything is odd or even. Okay. When you're dealing with numbers, with integers anyways, integers are odd or even. Fractions are neither odd nor even. So it is entirely possible and more than likely that your functions are neither odd nor even. In which case, if it doesn't come out the same, or doesn't come out the opposite, then it's neither. It's entirely possible it will be neither. So if you have a polynomial, it's actually pretty easy straight up to tell the polynomial if all the exponents are even. And what is my exponent on this one? X to the 0 power, which is even. If all my exponents are even, it's an even function. If all my exponents are odd, it's an odd function. If I've got a mix of odd and even, it's neither. The harder ones to tell are the ones that are not polynomials. Okay, sine and cosine. Okay, sine is odd, cosine's even. The only reason I know this is I can close my eyes, I can picture the graphs in my head, and I know which one's which. Sine is the one that passes through the origin. Cosine does not pass through the origin. Because the sine of 0 is 0, so it goes through the origin. Cosine of 0 is not 0, it's 1. It does not pass through the origin. One's odd, one's even. Because it goes through the origin, it has to. That's what it is. It's a symmetric method. Now, that's because I've got it memorized, and I've got, like I said, I can close my eyes and I can picture the two graphs, so I can figure it out the math very easily. Do you have to know all that stuff? Not necessarily. So here's a question I have for you. Can you come up with a polynomial that is odd and one that is neither odd nor even? Yeah, we just talked about it, so yeah. You know what to do to find odd polynomials and what to do to find neithers. Okay. Gentlemen, piecewise functions. A piecewise function is a function that is defined differently for different domains. It's one function that as the domain changes, the definition of the function changes. It's a piecewise function. Sometimes it's extremely important to use piecewise functions. And a lot of piecewise functions are extremely useful in real-world applications. You have a company, you have a catalog, you're buying stuff in. If you buy 1 to 10 items, it's one price. You buy 10 to 25 items, it's a different price. You buy more than 25 items, it's a third price. Guess what? That's a piecewise function based upon how many items you buy. Okay? There are times when you can take a function that's not piecewise, you wish to change it to a piecewise function or order to be evaluated. Absolute value. We hate absolute value in calculus. We must be able to work with absolute value in calculus. So what we do is we break it up into a piecewise function. We talk about, this part and that part, and we get rid of the absolute value function and break it into a piecewise function because that's the only way we can do what we want to do with it. You must take a regular function and make it piecewise. Take an absolute value and make it piecewise, or you can't do what we need to do with it. You can't. We cannot do what we cannot do what we do in calculus to absolute values. We must switch it. We must make it into a piecewise and evaluate each part individually. It doesn't work that much. So if I were to graph this, okay, everywhere x is less than 0, it's the line 2x plus 3. So that means it does not go through 3 because it's less than that and has a slope of 2. So that's one. That's that graph of that part of the function. Next part's x squared from 0 to x goes from 0 to 2. And it includes that spot and this spot. And then for the last one, ooh, it does not include that, my bad. You're right, positive slope. You're right. Sometimes it's hard when you're doing this. Let me get this last one. From x is 2, everything is 1. And that's an open circle there. Why open and closed? What's included, what's not included? Muy importante. Very important. Are these points included? If we're evaluating a function, whether or not certain points are included will be extremely important. What's going on at 0 depends upon whether we're coming at it this way or coming at it this way. Makes a difference. Okay, when x is 0. Well, when x is 0, it's 0. It falls under this function. But if we're just to this side, it's not. If we're just to that side, it's something different. It's really important what's going on there. It's what's important. It's what's going on at 0. It's what's going on as we approach that value. And knowing which one, where it exists and where it doesn't exist, where they have shared points, where they don't, is extremely important. Okay, so here's what I want you to do on this one. Come up with a piecewise function for this. Come up with the equation. Or I should say the function. Okay, so for lack of better terminology, the red portion of the line, I would say that that's x squared. Yeah, x squared. And the domain that goes with that, x is less than or equal to 0. Because I put in the dot down there, the red one's filled in, the blue one's not. Okay, the blue line is 2x. Because the y-intercept is 0, it's got a slope of 2. 2x, it's linear. And x goes from 0 to 2, non-inclusive. Which means that it's open-ended. Okay. And then last but not least, that's what? That's 4 when x is greater than or equal to 2. The horizontal lines are just fine. We love them. They're easy. Horizontal lines are easy. Straight lines are easy. We're not going to have a lot of them. Now, it is possible that both of those are open-ended. It could be that they are that. Now, due to the graphing program, it doesn't give me open-ended or not. You can't tell. But it is entirely possible that that does happen. It may be that what's going on here at 2, if that's the case. The function does not exist. It's not defined at x equals 2. If we have that situation where it's open-ended on both of those, that's entirely possible. What's going on at 2? It's undefined at 2. Doesn't mean that that's not an important place. In fact, it's actually more important because it's undefined there. Okay? Question? Compositions, composite functions. We're going to do a lot of stuff with composite functions. Okay? It is not fog. We're not in San Francisco.
What you said?
I said it's not fog. We're not in San Francisco.
Oh, that's your hand.
F composed of G. And I know you've done compositions before. Compositions are easy. F composed of g of x, or F composed with g. I like to say of. You can say of, you can say with. F composed of g. That means g is inside of f. So if f of x equals 2 and g of x equals 5x plus x squared, what is f composed of g of 3? What is g of f of 3? Are they the same? I don't know. Figure it out. Okay. So to do this, we need to do a couple of things. To do the first one, f composed of g of 3, we need to figure out what g of 3 is. Plug in 3 into g. 15 plus 9, that's 24, right? So that means f of g of 3 is f of 24, which is 22, correct? Okay. To get g composed of f of 3, we need to find f of 3. F of 3 is easy. 3 minus 2 is 1. So that's g of 1, which is 6. They're not the same. Now, if they were the same, and the same everywhere, if every input of 1, if g of x, if f of g of x is equal to g of f of x everywhere, and actually get x for both of them, then they're inverse functions. And that's it for today. We're going to talk